Thank you. I'm Bogdan, and I'm developer at Moya. That's everything interesting about me. And Moya is a ride-sharing service. We drive these big golden vans. Probably you've never seen them, because right now they are only driving in Hamburg and Hanover. But we also have an office in Berlin, and that's where I work, and that's where you can work also. And yeah. And our thing is what I'm going to talk about. It should have mentioned it earlier. We are using Rust with Scala inside the same application together in one server, and we are quite happy about it. And in general, our problem is we do optimization of breaks, which is an NP hard problem, and the main word about it, it's hard. And which means you can find a solution. There are many feasible solutions, and when you found one, you cannot know if it's the best solution usually until you checked every other solution. And to check every solution, it might take hundreds of years or something like this. So usually we don't solve such problems like optimally to find the best solution. Instead, we either try to find any solution that's better than some threshold, or as we do it in our case, we run solver for a few seconds and just pick the best solution we could find. And because of this, we try to check as many solutions as possible within a limited threshold, and this will be important later. But NP hard problems, they're very different, but solving them is quite a similar thing, and there are open source solvers for NP hard problems, which you can configure to run and solve your problem. And one of them is Optaplanner. It's an open source Java solver. And when we were only creating this optimizer, we were using Optaplanner, and it was quite nice because we could start quite fast, and it did all the hard part for us. And all we needed is to make a normal service with all the domain logic around it. Later, this Optaplanner became a problem because it's one black box. We just throw a problem into it, and it gives us some solution. We cannot tweak which solution, how to find it, and we cannot have some problem-specific features, and we have to agree with the speed it provides. So later, we wanted to rewrite our optimizer, and we wanted to do it in Rust. So we wanted to rewrite an optimizer to have something problem-specific. Because of that, we can make it faster, we can control what's happening, and important thing, we can know what's happening inside the optimizer. And we wanted to have it in Rust because if you look for a language that can squash as many operations inside the limited timeout threshold as possible, Rust is probably better than anything that's Java-based. And also we had memory safety and other nice things. And the most important thing is it's not the first optimizer in the company that was rewritten in Rust, and the reviews of this language were quite great, so we just tried to follow. And there's a problem. Rewriting takes time. Rewriting big things takes a lot of time. And if we look at our optimization service, our consumers don't think in terms of optimization problem. You don't need to read everything. It's quite boring. But the thing is, the optimizer, the thing that Optaplanner did, it's like this box in the middle. Before this, we get some requests. We consume some domain events from other services. We make synchronous call to external services. We get something from database. We aggregate everything. We kind of map it to the problem. And it's also not that easy. We have a decision tree inside. I'm not going to talk about it. Then we call optimizer, it solves something, we get response, and then we map everything back again, because our consumers don't think in the terms of optimization solution. And we send events, we write something to the database, and so on. And it's a lot of code. Rewriting this one box will provide us a lot of business value. We can get a better solver, we are happy. Rewriting everything else, it's useless. We are quite happy with existing code, and because rewriting takes time, rewriting something that doesn't provide any value is wasted time. And the bigger you changes, the more chance that everything will break at the moment of your switch. And if you just replace this huge service with a lot of external connections, we could guarantee that everything will break, and it means like passengers will be unhappy or something like this. So we wanted to avoid it. We wanted to rewrite only this one box, and we wanted to avoid HTTP calls within. So basically, we wanted to have Rust and Scala within one application. Is it possible? The title of the talk is already a spoiler. Yes, it's possible. We didn't know about this, so finding this answer took us about 5 minutes of Googling. Yes, it's possible. And we can do this with 3 letters, JNI, which is Java Native Interface. Basically, it's an interface that can connect Java applications to libraries that are written in C, C++, or assembler. And we can make calls in either way. And I didn't look much into the history of JNI, but it looks like it was created like together with Java to make it easier to move big applications gradually from C++ to Java. And it's still not forgotten now because of mobile applications. And probably mobile developers don't want to write Java, and I cannot blame them for this. Yeah. How to do these JNI calls? The original schema looks like this. You have a bunch of Scala code, you compile it, and you don't only get the Java application, you also create a header file, like C header file, for which you can then create an implementation with C or C++, compile everything together, and you will have a C++ library created to support JNI, and all this thing can go. It looks quite complex, especially if you remember that we want to write Rust and not C++. And these header files are quite useless for us. But Rust has a solution for everything, macros. Basically, if Java application thinks that something is created to support JNI, it doesn't need to know that it's not C. And Rust provides a few libraries to create with macros to create libraries that support JNI. We picked Robusta JNI because it doesn't depend on this header file. Instead, you need to match the class name and function names manually. But that's OK. You need to do this once and then just hope it works fine. It also provides some boilerplate. You need to copy-paste lifetimes and some macro calls, but that's fine. The main thing is you need to match the package names and struct name with class name and have the same function definitions. Also, Robusta JNI allows you to have store some data in this struct, so to keep the state between JNI calls, we don't need it. And yeah, we just provide one function with one string argument. It will be important later, and one string response, which is JNI result of string. So we can do this. We can call JNI. The next thing is how do we connect this optimizer with coordinator. Coordinator is a nice name for everything in the application except optimizer. Yeah. And yeah, it's quite a dilemma because we want to store optimizer and coordinator in different repositories. Basically, it's two different programming languages. Having them in one repository will be not nice. But another thing is we want to have Rust and Scala interface of optimizer. We want to store them in a single repository, so it's easier to keep them in sync. Also, we use Linux build of optimizer in the production, and we use Mac build of optimizer in the development machines. And we still want to use optimizer like in both development machines and production. So we need to connect them somehow. We need to decide how to store them in different repositories, and we need to decide with building and deployment. The solution is quite tricky. I made a schema. Here it is. Yeah. Basically, we store optimizer and coordinator in two different repositories. It's already nice. In the optimizer repository, we also have a very small Scala library that provides the same interface as optimizer. And all it does is loads the optimizer and forwards the request to optimizer. And then during the deployment, we compile optimizer in Mac and Linux builds, then just copy it to the Scala resources of the Scala library, and pack everything in SBT. And from outside, it looks like another Scala library, and coordinator thinks it's another Scala library. It doesn't know there's a Rust inside. And yeah, it works pretty nice. Next thing is passing data. The problem is, here's a mapping chart. How can we turn Rust and Java types between? Robusta GNI also does something with objects, but yeah, we have a huge structure with arrays and enums inside, and it's nested, and doing this mapping would be quite a tedious task. And then we need to do everything about the response. And our solution about this is to use protobuf, because we use protobuf everywhere else. Why not here? So in the same repository with optimizer, we also have protobuf definitions, and we generate Rust code from them and Scala code from them. They are all in the same repository, everything nice. So our wrapper library takes response, serializes into a string, and then calls optimizer with a single string. And optimizer deserializes it and uses everything else. So it also works nice. Another problem is error handling. Basically, if Rust application panics, Java cannot do anything about it. It just crashes. So the solution is quite obvious. Don't panic. It's a pop culture reference. Yeah. And that was surprisingly easy, well, except wrapping everything in try, because we already get a typed request with all the validation done on the Scala side, and because our Rust part doesn't call any external services, it's just a function, then the most reasons for panicking are gone, and we can just do it like this. And another thing is we return GNI result type, which can be success and which can be an error message. And if Robusta GNI receives an error, it just throws a Java exception we can handle on Java side, and it's also fine. Another thing, observability. One of the reasons for rewriting was we want to know what's happening. And if it's just a function that's a black box, then we don't know what's happening, and it was all wrong. And yeah, basically the solution is the picture. You shouldn't look at it so closely. It has no meaning. Well, okay. The robot symbolizes the optimizer, and the only side effects it does, except returning the response, is it writes logs. And the logs are in the same format as the ones Scala application writes. So for Kubernetes and for everything else, it looks like a single stream. And another thing, together with solution, it also remembers metrics and returns them together with solution. And Scala application can record them as it wants. So observability also solved. And one sudden nice thing that the change was even smaller, because with this thing we could run two optimizers in parallel, which is not like pick the best solution or so. We know that switching something introduces bugs, and because of this we could rewrite optimizer and run it in the shadow mode and compare results and fix the bugs. We found some. There were bugs, and then we did a real switch until when we were confident enough. And when we did a switch, no one else in the company noticed it, which was quite great. Yeah. So as a result, it works for about a year now. It works good. We had no problems after the initial deployment. Good is we get the best from the both languages. Bad is we have to know both languages, which is easy for us right now because everyone in the team knows them. It makes hiring harder. And the thing is, why would you do this? Well, you shouldn't do this from scratch, but if you had a big application in the one language, you really can migrate it gradually, and it will work fine. Yeah. So, thank you.
So you've mentioned that like one of the main reasons is that you want to solve bottlenecks in your current JVM architecture. So have you tried, for example, measuring that with implementing in the services themselves? I don't know, like a distributed tracing solution to see how that optimized, and would it work with Rust being in that context in JVM or interacting with JVM? Like how would you, for example, like how would you measure the efficiency of whatever resources you're using from Rust?
Yeah, measuring these two things were quite hard, like comparing, because we also changed the algorithm. And one result is we looked at metrics and we could find good solutions like several times faster. And for us, it matters a lot because we are called synchronously, and finding great solutions fast is nice. And yeah, because of rewriting, we could also get the conditions when we exit earlier, which was also fine. And yeah, we could just check the number of steps and mutations per second, and with Rust it was better. Although it's hard to compare because we have different mutations, and like it depends on the algorithm.
Nice, thank you.
Yeah, I do understand that question. And then
Thank you for the talk. You've explained how for integrating Rust in this way you had to use for Robusta, you had to like write the function headers and so on. Have you weighed converting to remote procedure calls and then having the Scala parts integrate with Rust in that way? I wonder what were the advantages and disadvantages of both approaches.
Mm-hmm. With remote procedure calls?
I mean, instead of integrating Rust within Scala, just making it into another
deploy it separately and make HTTP call.
Or other protocol.
But it's a network call with network latency, and we wanted to avoid it. And yeah, we wanted to for all the coordinator parts to make look that nothing changed.
Interesting. Because
This person, then you, and then I think.
You mentioned like optimization, but like JNI codes could be quite expensive compared to normal Java functions. Do you have any like numbers, like, because do you call it often to JNI codes in general, or?
Yeah, in general we have one GNI call per about 30 seconds, so for us it wasn't a problem.
Okay.
Yeah,
then
if
it's
you do something inside high load, so that's something gets called often, then yeah, maybe you shouldn't look at it.
yeah. Okay. Thank you.
Do you run this code on the cloud, or this is running on, because I don't understand what it's doing the company. It's like there is a track that needs to do some stops. Where do you do the calculation? Is on the cloud in servers, or is on the car?
It's calculated in Kubernetes.
In Kubernetes
so
on the cloud.
yeah, on the backend.
Can you try to run this on smaller devices without an internet connection?
We don't have such a problem. Like, we need to coordinate the fleet, and you cannot do this from within one vehicle because you need to know
what are the
state
others?
of the whole fleet to coordinate it properly.
Yeah, so you need internet.
Mhm.
Okay.
Yeah.
I think we're out of questions. If you have more questions about the talk, you have now 10 minutes to ask the first few presenters a few things and grab a drink, and then we are back at 8:30, maybe 8:30. Sounds good. Thank you.